The next example that we'll look at is strain example number 12, and it's another indeterminate problem. This one's arranged a little bit differently, though. The process is the same, but the details associated with the geometric compatibility equation on this problem are different than they were in the last two. So the process for solving the problem is the same, though. Start with statics. If that doesn't work, then introduce geometric compatibility equations, and then finally constitutive relationships or Hooke's law. So the problem asks us to determine the force in each portion of the rod shown below. The two rods are made out of the same material. So when you look at a problem like this, sometimes it can be challenging to decide what it is that you're supposed to draw the free body diagram of. So it works out that this little interface plate here that I'm highlighting there in green is the element that we want to highlight as our free body diagram. So I'm going to take that and I'm going to move over here to the right, and I'm going to draw a free body diagram of that plate. Now, you see the load that's applied there, 20 kips pushing to the right. There are two other loads on there as well. The segment of the rod between points A and B is exerting a force, and the segment of rod between points B and C is exerting a force as well. Now, if we push this interface plate B to the right, then segment AB has to go into tension and segment BC has to go into compression. So I would be tempted to draw a force over here, P sub BC pushing to the left because it needs to be into compression. But what I'm going to do is instead stick with my sign conventions, and a rod is in tension until proven otherwise. So if this rod BC is in tension, that means that it's pulling on this interface plate. It's pulling to the right, P sub BC. If I assume that rod AB is in tension, that means that it's pulling on the interface plate as well. So P sub AB pulling to the left like that. Now, like I said, I expect that segment BC will be in compression. So if that's true, then when I solve for the force P sub BC, I should get a negative answer. All right. Now, for this part here, I can use equations of statics. Sum of the forces in the x direction is equal to 0. And what I end up with is P sub BC plus 20 kips minus P sub AB is equal to 0. I could write the sum of the forces in the y direction, but I would end up with 0 equals 0. And I could also write the sum of the moments about some point, but since it's a concurrent force system, then I would have 0 equals 0 from the sum of the moments as well. So I have one useful equation, I have two unknowns, I have more unknowns than I have equations, so therefore I have a problem that is statically indeterminate. So when I have that situation, then what I know is that I have to look at force deformation relationships and geometric compatibility. So let me shift my attention back over here to the drawing on the left. I'm going to erase that little bubble that I drew earlier. And if I push a force on this on interface plate B and the force goes to the right, then I would expect that that plate is going to move to the right as well. So we originally started off with this, and let me draw this line in here as green, kind of shaded in there lightly. I'm going to end up with this rod going to the right, and here is my interface plate, and then here is segment BC. So what I have here is a displacement. Let me zoom in on that. I'll call that displacement delta C. And what happens is that delta C is moving to the right. That's a displacement. Why did I call it delta C? It's delta B. Apologies. Delta B, not delta C. Delta B. So I write C again. Delta B. Now, delta B, that's a displacement of point B, and it's moving to the right. That corresponds to a stretch of segment AB, but it corresponds to a contraction of segment BC. And since it's a contraction, it gets a negative sign on it like that. So then this becomes the geometric compatibility equation with Hooke's law built into it. So that's the geometric compatibility equation. And then now what we can do is substitute Hooke's law. So we know that PL over AE is equal to delta. So that's AB. And then this is going to be minus PL over AE for segment BC. Okay. Now we can work with that. Let's see, if we do some substitution in here, we know that we're going to have P sub AB times L sub AB, which is equal to 6 inches. We know that we have A sub AB, so we have pi over 4 times the area, 2 inches squared. And then we have E sub AB. And that's going to be equal to minus P sub BC times 6 inches divided by pi over 4 times 1.5 inches squared times E sub BC. Okay, now we can do some canceling. 6 and 6 cancel. We know that pi over 4 and pi over 4 cancel. And it works out from our problem that it says that the two parts of the two rods are made from the same material. So that means that E sub AB is equal to E sub BC. So those go away as well. So from this, we end up with a relationship that PAB divided by 2 squared, which is 4 inches squared, is equal to minus P sub BC divided by 1.5 squared. 1.5 squared is 2.25 inches squared. So let's see. If we put the 4 in there like that, divide by, we end up with P sub AB is equal to minus 1.778 P sub BC. Okay, at this point, we're going to go back up and we're going to take a look at our statics equation, this equation here, and we're going to bring that down below and use that. So P sub BC plus 20 kips is equal to P sub AB. So P sub BC plus 20 kips is equal to P sub AB. Now what I can do is I can take this and substitute in here. And when I do that, I end up with P sub BC plus 20 kips is equal to minus 1.778 P sub BC. Whoops, why did I do that? P sub BC. So I end up with, let's see, 2.778 P BC is equal to a minus 20 kips. So let's see, if I divide 20 by 2.77, then I get P BC is equal to a minus 7.2 kips. Or I would say that's equal to 7.200 kips compression. Okay, cool. Now what I can do is I can solve for P sub AB. So let me go ahead and just sketch in a division line there, work over here. So I know that P sub AB is equal to minus 1.778 times P sub BC. So that's minus 7.200. So what I end up with there is P sub AB is equal to 12.80 kips, and that's in tension, or that's positive. So final answer, we end up with P sub AB equal to 12.80 kips in tension, and we end up with P sub BC equal to 7.20 kips in compression. Okay, thanks.